Giant covalent structures. Sodium chloride forms giant ionic structures because the bonds between sodium and chlorine are ionic compounds. For covalent compounds, they can either form molecules, like what we have seen in the previous classes, or they could form giant covalent structures. For example, in diamond. Diamond is basically formed from carbon, and each carbon atom is covalently bonded to 4 other carbon atoms. Focus on this carbon atom here. This one represents carbon atom. And the lines, of course, represents a covalent bond. Now, when you focus on this carbon atom, we'll find that it is covalently bonded to 1, 2, 3, and 4 other carbon atoms. This kind of arrangement is known as tetrahedral structure. And it repeats itself over and over, because you can see when you focus now on this carbon atom here, it is still covalently bonded to 1, 2, 3, 4 carbon atoms. So the pattern repeats itself over and over and over to form diamond. Now, because of these, diamond has several properties. One, it is very hard because of the uniformity of the arrangement of atoms. Secondly, it has very high melting and boiling points. The next example of a giant covalent structure is one of graphite. Now, as for graphite, we have carbon atoms again, but this time they are arranged in layers that are hexagonal. Can you see this as 1, 2, 3, 4, 5, 6? This is 6-sided structure, means it is a hexagon. So they are arranged in hexagonal layers. Now, since carbon is tetravalent, that means it has arrangement of 2, 4. Since 3 electrons are used in sharing, we have 1 extra electron left. In this case, the extra electron responsible to bringing some weak van der Waals forces of attraction between the layers. This makes graphite soft, unlike diamond, which is hard because of the uniformity of the arrangement of atoms. Also, the extra electron that is left is responsible for conducting electricity and heat. And therefore, unlike diamond, graphite is a good conductor of electricity. Another example is silicon 4 oxide. It forms a giant covalent structure whereby each silicon atom is covalently bonded to 4 oxygen atoms in a regular pattern to form the silicon 4 oxide structure. And that is why silicon 4 oxide has high melting and boiling points, and also it does not conduct electricity or heat. Physical properties of covalent substances. The first property is solubility in water. Covalent compounds do not generally dissolve in water, so we can say that they are not soluble in water, which is insoluble in water. However, some are just slightly or sparingly soluble in water. Next property is melting and boiling points. Covalent substances either form simple molecules, which we say simple molecular structures, or they may form giant covalent structures or giant atomic structures. For simple molecular structures, these ones have generally low melting and boiling points, while the giant covalent structures have high melting and boiling points. That means they require large amounts of heat to reach their boiling point. Next is electrical conductivity. Covalent compounds do not conduct both heat and electricity. Basically, we could have these viewed from different perspectives. Now, the covalent compounds such as carbon 4 oxide, sulfur, do not conduct electricity or heat. However, we have some special cases such as water. Water conducts electricity because it is what we call a polar solvent and therefore behaves like an ionic compound in a way. But generally, covalent substances do not conduct electricity. This is just an exception.